Hi, this is Wes Simpson with another edition of the Summer Sessions on Media over IP, brought to you by AIMS in the VSF. With me today are Anup and Rahul from Cisco, who are responsible for the media and entertainment vertical within Cisco. And they are going to be talking about All Mobile Video's new ST2110 OB van. Welcome, Anup and Rahul.
Hey, Wes.
Hi guys, welcome. I'm glad you're here today on a nice sunny day, right?
Yes, looks like all of us are sitting somewhere at the beach side.
I like it. I like it.
soaking all the sun we get, right?
There we go. All right. Well, let's get started.
Thank you. Thanks, Wes. So first of all, good morning, good afternoon, good evening to everyone, wherever you're joining us today from. So today we are going to talk about a case study for a fully 4K UHD capable OB van for one of our customers, All Mobile Video, and how Cisco's IP Fabric for Media solution was able to address some of the key requirements and use cases for this customer. So a little bit about the customer here. So All Mobile Video is one of the biggest production facilities in New York. And they've produced and transmitted some of the most prestigious events, including the Oscars, the Grammys, Adobe Max and Summit, etc. They basically cater to a variety of pre and post production use cases, depending on their client needs. And as you can see, as the business was expanding, what AMV wanted to do was, build a fully 4K UHD capable OB van to target events such as, sports games, concerts, and even, emerging streaming services like Amazon Prime Video, Netflix, etc. As you can see, they wanted to use this OB van for a variety of use cases. And that's why they wanted an architecture which was very dynamic and flexible, and one that can support the ever-changing client needs. Which also includes, having to do some pre and post event shows and having the capability to extend production beyond the truck walls. Yeah? So let's look at what it boils down to when it comes to the core technical requirements, right, for this customer. So what the customer needed was basically a network based on COTS equipment. This is to make sure that they can leverage this equipment for a variety of use cases and are not limited to a certain specific functional box. Also, they wanted to make sure they are deploying standards-based fabric based on the new SMPTE 2110 standards and NMOS, etc. Also, as you can see from their use case, they wanted a very flexible and scalable architecture. Because they cater to a variety of use cases. They go to sports events, they go to concerts. The network had to be very, very flexible and dynamic. And then one of the most important things that they wanted was to simplify their day-to operations, to make sure that at any given point of time, they have insights into the network and fabric. And then they also needed a scalable PTP implementation so that they can connect a lot of endpoints to the switches. And then they wanted to make sure that the network is secure, and they wanted to have granular access, the capability to make sure that they can deny or allow only certain specific hosts and flows through the network. Okay. And then obviously redundancy and reduced footprint was one of the requirements as well. So let's look at the slide. And on this slide, as well as the next few slides, we'll look at the high-level design of the architecture, and also deep dive into some of the key requirements and how Cisco's IP Fabric for Media solution addressed those. Okay. So as you can see on this slide, the customer wanted a scalable and flexible architecture. And what we went with and what we call it is like a hybrid spine leaf architecture. Okay. Made of 9508, the Nexus 9508R chassis as the spine with 36 port 100 gig line cards and 93180 YCFX Nexus switches as remote leaves. Okay. So this architecture gives you the capability and the flexibility to connect endpoints directly to the spine, which resides inside the truck, and to connect endpoints to the remote leaves, which are outside the truck. And one important point, again, I would like to bring out here is, they went with the 100 gig line cards as of now, but the same 9508 chassis can be reused and can be upgraded to 400 gig line cards as and when the customer would need probably in the future. Okay. And another thing I'd like to bring out here is the broadcast controller was the GV Orbit. The GV Orbit completely integrates with our Cisco's data center network manager, which is the DCNM. And DCNM is basically a software, a VM, running on a box, which helps with day 0 to day 2 operations for our Nexus switches in the fabric. And this whole network is capable of sending, flows from all the way from 1.5 gig HD to 12 gig UHD. And depending, as you can see from this slide, there were a number of glass value endpoints, and depending on that, we required some port capacities to be 10 gig, 25 gig, 50 gig, as well as 100 gig. And we also required a long-range connectivity between the spines and the leaves. Okay. And then another important thing I would like to bring about is, the Cisco's NBM technology, which is developed by Cisco specifically for our media industry. This is to provide non-blocking fabrics for carrying uncompressed video, audio, or any ancillary flows over the fabric. Okay. And this gives you a little bit more overview of, what were the other endpoints, etc., that were used in the system to build this OB-WAN. And if you can see from the list on the left-hand side, there was GV Orbit and Cisco DCNM for control and monitoring. The IP switches were the Cisco's Nexus 9508R and the 93180 YCFX. The cameras were LDX IP100, switches, replays, there were gateways, and multi-viewers, etc. All of this running over the Cisco's IP fabric for media. And with this, I'd like to hand this over to my colleague Rahul, who will go over the challenges that we faced for this customer and how we address them using our solution.
Hey, thank you, Anup. So as Anup described, right, the system had to be scalable and non-blocking. And it not only stopped, it did not stop there, right? But we went on from designing the entire fabric to be non-blocking, as well as think about timing, right? With any 2110 deployment, you have to make sure that all these endpoints are synchronized to a nanosecond accuracy. And the way we went about doing that was through PTP. And so I'll talk about how did we scale PTP, right? And then we'll focus more around how did we go about simplifying some of these operation challenges, and then touch upon security. So Wes, as you move on to the next slide, let's talk about this whole system and how did we go about addressing each of these challenges, right? Now, this is an interesting, so even before we started this project, right, one of the biggest requirements, when you essentially use a COTS-based network to transport uncompressed video, is that the entire system has to be non-blocking, right? Because you come from an SDI router, which is traditionally non-blocking, to now an IP network. Now, what people may not realize is that, hey, while each individual network switch can be non-blocking because it can do line rate, multicast forwarding, and replication. Now, as you start building networks, like how you have the stage box, a leaf connected to the spine, and you have multiple links going from the leaf to the spine, it reminds me of taking two SDI routers and you have tile lines between them, right? So there is this whole requirement that, hey, how do you make this system non-blocking, right? It's not just about having each individual entity non-blocking. Now, to describe the challenge we face, let's take the scenario, right? So in this scenario, let's assume that I have 4 sources. Each one is configured to do UHD. And again, for the sake of simplicity, let's assume that the links between the stage block, leaf, and the spine were 40 gig, right? So if you look at it, right, theoretically, anyone looking at the system would say that, hey, yeah, this is a non-blocking system because you have as much as 40 gig of sources, because I have 4, Ultra HD sources in the network, and I have about 120 gig of bandwidth from that leaf to the spine. So this should be non-blocking, right? Now, what people, as you start talking to a lot of broadcast engineers or network engineers for that matter, they don't realize is that when you have multiple paths, going from one network switch to another network switch, the way protocols go about routing each of these sources to the destination, all depends on what we call as, a hash function, right? So now, as you advance these slides, Wes, you'll notice that what could potentially happen is, as you go ahead, you keep advancing, there could be a possibility that all of your video ends up taking the same path, right? And that path can become blocking. You see, that's because networks themselves do not know, okay, this particular 2110 feed is of a video, this particular multicast feed is of an audio, and this is a particular feed that belongs to an ancillary, right? It's just going to randomly pick paths, and you could end up in this situation where all videos takes the same path, and that way it could become a blocking system. And this was the challenge, and the way Cisco went about solving this challenge is through NBM, right? So as you advance the slide, Wes, you'll see, if I enable NBM on the system, what we're really doing is we're making this entire network bandwidth aware. So what it means is that as you start routing different flows from the leaf to the spines, now you see with every request, the system realizes, hey, by the way, that this particular flow belongs to a video, this belongs to an audio, this belongs to an ancillary data. And because this whole system is bandwidth aware, you get a much cleaner distribution of traffic along these links. And that was how we went about ensuring that this whole system remained non-blocking, right? And as a result, now the customer can confidently go and connect these stage boxes and connect a bunch of their cameras, and not having to worry about, hey, will I ever run into an issue where one of these links become blocking? And I want to reiterate this message to the audience, saying that, hey, because I've always said, right, people say, what, I can just throw bandwidth at the problem. Oh, you're running into a blocking issue, just add more links. You have to realize that, it's adding more links only reduces the probability of reducing the fact that this problem would not take place, but it's not going to completely avoid it. And to completely avoid it, you need some kind of an intelligence, and that's what we did with NB. So that was challenge number one. Now, this was a tough one, right? Challenge number two is, okay, now that we've addressed flows, what about timing? You see, media, SMPTE 2059-2, it mandates that the offset, the PTP offset should be less than plus or minus 500 nanoseconds. Now, it's relatively very easy to do this at a low scale, but for this customer, we had to do this at a very large scale because they had lots and lots of endpoints that were connected directly to that 9508 chassis. And most of them were also working in this breakout mode, right? So you could have a single interface, but broken out into 4 lanes. So that increases the number of PTP sessions by 4 on every port. So what happens as a result is that a single line card could be broken out to 144 PTP enabled interfaces. So we had to figure out, hey, how do we go about ensuring that you can scale PTP? And this is something that we're really proud of, right? So we went and we developed a feature again for the broadcast industry where rather than running the entire PTP process on the CPU of, it's called the supervisor, for those of you who are not familiar with, a modular chassis. So rather than running it in a centralized, processor, what Cisco did is we offloaded the PTP functionality to each individual line card CPU. So this automatically increased the scale, right? Because as the only way you can increase the scale is by going with a distributed architecture. So we don't have a single point that is responsible for talking PTP with every single client that's connected on the chassis. Now, as soon as we did that, right, we took this PTP process and we executed it to run on each and every line card. You see, an 8-slot line card has, an 8-slot chassis has 8 line cards. Now we are able to individually scale each of these line cards to that 144 PTP sessions, or the entire chassis can now support about close to 1024 PTP enabled interfaces, which humongously benefits that whole requirement of enabling a large scale PTP deployment, yet meeting SMPTE's accuracy requirement of all of this being within plus or minus 500 nanoseconds. And now you have a system that is intelligent and scalable with both flows as well as PTP. So that addresses the second point. Now coming to the third challenge, right? So this is where even for the customer, it was the very first time a lot of them were interfacing with an IP system, right? All of them have really good knowledge on broadcast, but did not have enough exposure to IP. So they really wanted a single pane of glass to monitor the application, which is 2110, all the way from the endpoints. When I say endpoints, it's the IP gateways, the cameras, and how these flows are traversing the network. So to be able to monitor the health of these 2110 flows from the network. And the way we went about doing this for the customer is leveraging a technology called streaming telemetry. Now, what is streaming telemetry, right? Now, if you go back a few years, the way networks were constantly monitored is that you had an entity that queried the network, right? Every 5 minutes or every 30 minutes asking, hey, how are you doing? And the network says, yeah, I'm doing all right. And this polling wasn't fast enough for, media, because we're all talking about real-time video, right? You're talking about video that's going on air. So we had to really change the way, the health of the network and the flows are propagated to this system that's monitoring, the overall health, right? And we leverage streaming telemetry as a result. So what happens in this architecture is that each individual network switch, be it the stage box switch or the spine itself, that's constantly streaming information out to DCNM, which is then feeding that information to GV orbit. So GV orbit becomes a single pane of glass where the broadcast team can, get this end-to-end visualization of how the flows are traversing the network and the health, the bandwidth usage, the CPU utilization, the memory utilization, all of that is fed to GV orbit, and all of this is done in real time. So that solved, what was one of the biggest challenges, on getting this complete visibility into, hey, what's going on in the network. Whereas as you advance these slides, if we go to the next slide, we'll talk about one more requirement was around the bit rate, right? See, you're always talking about 2110 flows, right? How do you know the camera is actually sending? If the camera is configured to do 3 gig HD, is it actually transmitting 3 gig of traffic or close to 3 gig of traffic on the network, right? And we've added the ability to not only monitor the interface stat, because the interface could have multiple flows on it. You can go as granular as looking at the stats on a per flow basis, right? So you get the stats of the video flow, the ancillary flow, the audio flow. And again, right, through streaming telemetry, all of this is fed to DCNM, which in turn feeds all of this to Orbit. So this is what I call something that is always an afterthought for a lot of our customers, which shouldn't be the case, right? Because I get it, right? For a lot of our customers who are making this journey from SDI to IP, like AMV, they're more focused on making sure that the system is scalable. Hey, all I need to make sure is that my video and audio works, right? But one thing you never had to worry with SDI was security, right? Like no one could go and hack an SDI router or connect a laptop to an SDI router, right? But fast forward in the IP world, nothing is going to stop me from taking my laptop, running a Wireshark capture, and plugging in and trying to subscribe to something that's being recorded, right? You could have the season finale of a pretty cool series that's being recorded, and someone can just take a copy of that video. So security is a factor that I would encourage everyone to make it a top priority. And just like as we started speaking with AMV, they also realized this. And this becomes more so dangerous with this whole stage box concept, right? Because as long as it's in the truck, you would think, hey, it's still relatively safe because no one who's unauthorized is gonna walk inside the truck. But because you're extending your network outside the truck and you're putting you're extending it to some of these areas that are accessible to anyone, what we ended up doing is we went with a model where by default, everything is denied, right? So nothing is allowed to participate in the network. And GV Orbit becomes, what I call the entity that is responsible for identifying who is allowed to participate in the network. So leveraging a very simple API call, GV Orbit pushes this, what I call a policy, onto Cisco's IP fabric and instructs it saying that, hey, these are the list of endpoints that can send traffic. These are the list of endpoints or devices, destinations that can subscribe to traffic. And those policies are then enforced on the network. So what it means for the customer is that because you have this, by default, everyone is denied and you're only allowing, what devices are authorized, it gives them some peace of mind that, hey, no one will be able to go and, connect something that's unauthorized to either send some traffic or subscribe to something that they're not allowed, right? So security became, it went from a nice to have to something now you needed it. And we've just made all of this extremely simple with this policy model through Cisco's IP fabric for media. So that, addresses that portion. And finally, we took security another step, right? It's not just about allowing a device to transmit or allowing a device to subscribe to a flow. But remember, right, as you design a system, you design it to be non-blocking. So you go with the assumption that, a certain endpoint is only going to transmit traffic at a certain rate. right? Because you, at the end of the day, you design the system to, allow for this to happen. But what if a camera that was only supposed to do 1.5 gig HD accidentally is doing 3 gig HD, right? So it is sending more traffic than what you intended it to send. So rather than allowing that stream to go through and oversubscribing the network, what we do with Cisco's IP Fabric for Media is we enforce that camera to only send, that much amount of traffic it's allowed to. And again, for us, GV Orbit was, that entity that defined, hey, how much traffic can a given camera send, right? So Orbit went and pushed ahead a policy called flow policy that defines these parameters. And we are able to detect, right, hey, is that camera sending traffic at that rate? And if it is sending an excessive rate, we protect the infrastructure by blocking that camera. And we send a notification back to Grass Valley saying that, okay, someone is trying to, consume or rather transmit more traffic than they're not allowed to, right? So then it could either be an accident or, someone did by mistake, or if someone is trying to do it because they want to, oversubscribe the network, in any case, you're protected, right? And you're notified. So if I have to summarize, the challenges that were presented in front of us was around the system being non-blocking, the ability to scale PTP and simplify operation and secure the infrastructure. So we've gone about doing that again, right? We addressed the non-blocking portion using NBM. We went about scaling PTP by ensuring that we have this PTP offload. We went about simplifying operations by ensuring that you have this telemetry-based real-time notification that's fed all the way to GV Orbit. And finally, we went about securing the infrastructure through these policies, right? Through which you could enforce who's allowed to participate in the network and what bandwidth they're allowed to transmit to and so on. So Wes, if I have to, we quickly summarize everything that we've done for this customer, again, through our partnership with Grass Valley. Now they have a system that is reliable, is designed to scale, and is designed to be flexible, right? And like Anup was pointing out, it was really, really important to ensure that whatever they build today, they can seamlessly expand, or they could, bring in newer use cases onto the system. And we've put in the infrastructure there that, they can just take it and grow as the business grows as well.
That's great. Thank you very much. So have you actually been able to go out and see this vehicle in action, or has COVID prevented you from going out and taking a look?
Yeah, well, we have actually, we're all set to roll this vehicle into NAB this year, but we're all in the situation where unfortunately that couldn't happen. So for now, it's all been remote updates and just working through them online.
That's unfortunate. Well, hopefully they're getting some good use out of it. So
I know, right?
Yeah. So I see you guys have done a lot of things to make the life of the engineer in charge on the OB van make that person's life easier, giving them some tools and some other things. What else can be done to simplify their life and to make their job easier and more efficient?
That's a great question, Wes, right? To begin with, right, some of the tools that we've exposed to this engineer was all around, hey, being able to traverse, how this flow is going from, say, a camera all the way to a video switcher, right? So giving that flow visibility, that's a good starting step, so that, that addresses some of the concerns that the engineers have, that, hey, how do I know what flows are traversing where in the system? But as we, develop more features for our customers, what we've also done is we've enabled this feature called RTP flow monitoring. Now, given all SMPTE 2110 flows are RTP flows, something that makes our ASICs really unique is that we can do deep packet inspection. So we can go all the way into the RTP header and thereby monitor the sequence numbers of RTP packets. And as we detect missing sequences, we can create an alert saying that, hey, you're losing packets, right? Now, to give you an example, let's say you have the camera connected to a stage box, and let's say the camera is recording traffic that's being fed to the video switcher, and then the switcher starts reporting some errors, or you see bad video on screen, right? Now, how do you know, right? Is the problem with the camera? Is it the problem with the stage box switch? Is the problem with the links between the stage box and the chassis, right? Now, given that our switches can do deep packet inspection, we can quickly pinpoint where along this path where is the errors being introduced. So you see these capabilities that we have in our ASICs, we're now turning them into use cases for customers wherein they can simplify the amount of time it takes, right? Should something go bad, like you have a bad cable, being able to pinpoint where along this path is this problem happening. So this is one of several examples that I can provide where we're all focusing on leveraging the capability that is there on the silicon and software to really simplify the amount of time the engineer takes to figure if something were to go wrong, where exactly it's going wrong.
And just to add to that, right? I mean, if you've ever troubleshooted a multicast issue, it probably sometimes takes hours to get to know even what is happening, where it's going wrong, right? With this feature, we can actually reduce the mean time to resolution to even seconds, because we get instant notification of not only when we detect the problem, but where exactly that problem is occurring in the network.
Yeah, that sounds like a big help. So one of the things that's always interested me, this seems like a very capable vehicle all by itself. How does it go about moving out of being an island unto itself and cooperating with other vehicles or infrastructure that may be installed at a venue? How do all those connections work?
Again, a great question, Wes. I'm a firm believer that as this industry transitions to IP, you have to make the best out of what IP gives you, right? Which is flexibility. And what this architecture really enables, this customer to do is to take that truck, and let's say they want to connect to, an IP infrastructure that's laid in the stadium. You are essentially extending the network on the truck with that of that stadium. Yet, through these security policies, right, the broadcast operator in the truck can actually define what streams can be either sent to that third party, or what streams you can ingest from that third party, right, through these granular rules. So net, we have the ability to extend this NBM, this whole bandwidth awareness across systems. So if there's another OB truck that shows up, let's assume that that's also an IP-enabled OB truck. You can interconnect these trucks and make sure that these tie lines are also bandwidth aware, right? And that is so you don't have to worry about, hey, will I be oversubscribing these tie lines, right? These IP tie lines. And the other beauty about the ASIC functionality that we have on the Nexus 9K is we can do multicast NAT. So this really helps, right? Let's say an OB truck shows up and they happen to be using an overlapping address, because at the end of the day, the address has to be unique, right? Because let's say they're using a certain address that belong to certain cameras, but I'm using that same multicast address for a different application. I can still ingest those flows to my truck, leverage this feature called multicast network address translation to translate that IP addresses to a non-overlapping range, and still route that signal to any destination in my truck, right? Mm-hmm. And I can even do that if I'm distributing content, right? Or if I'm handing off content to third party, I can NAT, the 2110 flows to a completely different IP schema and send it to them. So this serves two purposes, right? It protects you from this You don't have to worry about, hey, what happens if address space is overlapping? But it also brings in some amount of security, right? Because sometimes you do not want to expose, hey, what addresses that you're internally using to some third parties. So that becomes an amazing use case where I can totally do that and hand off content to anyone who's interested in, right? So those are the capabilities that's enabled on the software and the ASIC that's inside the truck. They're not using it today, but again, the whole goal about IP is also future-proofing your investments. So when the time comes when the customer says, hey, I have this use case, yeah, they don't have to worry about spending more money and getting different switches, right? We already have the best of breed of networking gear that has all of these capabilities built in.
Well, that sounds like a pretty impressive vehicle, and I hope you guys are going to get a chance to go to an event where they're actually using this. It sounds like you put a lot of work into this.
I know.
Yeah, we can't wait.
All right. Well, thank you so much for joining me today. I really appreciate your time.
Thank you, Wes. We enjoyed the conversation as well.
That's great.
Yep, same here.
Yeah. So do you guys have any idea where this might be getting used in the near future?
Well, do you know, Anup? What are the first games?
I think because, I don't know, because of COVID-19, everything got delayed a little bit.
Okay.
Hopefully, yeah.
We're excited to see our technology in use, right?
I'm going to have to watch that one live. Well, thanks again, guys.
Fingers crossed. No problem, Wes. Thanks.
Bye-bye.